direction is from the what? From the neutral axis, and it's pointing away from the what? Center of curvature. So this is over IZZ. So this will be equal to MZ y over IZZ. It's positive now because minus multiply minus is positive. Now it's become what? Tensor. Okay. So the y direction pointing towards the center of curvature is positive, pointing away is negative. But I don't want you to remember that. Too complicated. Okay. I want you to remember something simple. Okay. What is something simple? If you look at the moment arrow or moment vector MZ, right? Head of the moment vector is compression. Tail end of the moment vector is what? Tensor. That's it. Nothing else more to remember. Repeat again. The head end, okay, the head end of the moment arrow or moment vector is always compression, right? Wait. And the tail end of the moment vector is always in what? Tension. Done, or tensor. Okay. So don't worry. Do not worry about this minus sign. Okay. Is it minus? Is it plus? Where's the center of curvature? Sometimes you have structure that you cannot visualize the deformation. It can look like this. Where's the center of curvature? One is here, one is here, one is here, one is here. You get confused. Yes or no? You get confused. So don't bother. Okay. So you look at the deformation. You look at the moment arrow. Now, I'm going to throw this out in another way. So now, if you have your structure looks like this now, your deformed structure look like this now. Now let me draw this properly. Okay. Now your structure deformed like this now. Okay, your structure deformed like this now. Right? And then this is your neutral axis. Right? And then by looking at this, so my points did not change. So this is my point alpha, and this is my point beta, right? So to bend this way, our moment vector need to be in this direction, right? So we know the head of the arrow is in compression, right? The head, and then the tail end is in what? Tensor. So if you're going to apply the formula, now where is the center of curvature now? At alpha side or beta side? Anyone? Where's the center of curvature?
Beta.
Yeah. So now this is the center of curvature. So the center of curvature will dictate where is y positive. Okay. So over here, this side, this direction now, y is positive. When pointing towards the center of curvature, it's always positive. Now y is what? Y is negative. So for this case, when we look at it, stress x alpha is equal to minus mz over izz. Now alpha, y is what? Y is negative, right? So this will become mz positive mzy over izz. So now this become tensile, which is true. And then stress x at point beta is equal to minus mz. Now y is what? Positive. So that's where you have minus mz multiplied by y divided by izz. Now you have what? Compression. Okay. So I think don't you think so? The easier way to calculate is the head of the moment arrow is compression. The tail end is what? Tension. Straightforward. Later on, we are going to do bending in two different axes, okay, which is unsymmetrical bending. So these are your MZ. Okay. Question so far, anyone, please? Anyone? No? Okay. So the next question is, remember, I put this like, what is this stress X? Okay, what? So where is the orientation? Okay, where is the orientation? Okay, where is the orientation of the stress X? Okay, so I'm going to copy this diagram. Hopefully it work. Usually copying don't work, especially for strength of material. So you paste. Sorry, I'm thinking about math. Unlike math, it always work. Right? So if we were to take an element, okay? Take an element. We draw an element down here. Okay. So an element is a small square. You designate as an element, or when you put strain gauge in that area. Okay. So bending moment is greatest at point B. Okay, someone. Okay. So over here, I call this element at B. Okay. So if I draw a big element, I'm going to draw a bigger element now. Okay, so this is a big element. So this is our element B. All right. So if this is our transformation, X and Y. So normal stress in the X direction. Why is it normal? Because it is perpendicular. I should use a different color. It's perpendicular to the element surface where the plane intersect the X plane. Okay. And then in the other direction, this is your stress in your Y direction. And why is it sigma? Because it's perpendicular. Then we have our shear. Remember our shear? So this is shear. The plate intersect the axis y stress vector. Your shear, the plate intersecting the y, the vector is x. Okay, so this looks familiar, yes or no? Right, I think you all see that in the shearing stress. Okay, so we are calculating stresses in the x direction down here. Okay, that's where we say that stress x is equal to minus mz over izz multiplied by what? Y. So this is a straightforward one. Now we're going to view this structure now. Okay, we're going to look at the cross-sectional view. Right. So if we look at cross-sectional view, so this will be like what we've seen before. So this is my transformation now. So this will be my Y. This will be my Z. This is my rotation in my X. Okay. So now we are looking at a cross-section view. So our cross-section view, we see this. Okay, for example, we see this, right? So this is our cross-section view. Okay. Then we're going to draw our stress field or normal stress distribution. Okay. So this is a new diagram. I think most of you have not seen it before, or maybe some of you have. So on this axis over here, this is our stress in the X direction, right? Stress in the X direction. Then over here, this is our Y. I'm trying to eyeball this straight. So on the right hand side, your stress is positive, which is tensile. On your right hand side is tensile. On the left hand side is compression. Right? So if we follow how the stress or the force is applied, we know on top over here will be compression, and we know down here will be tensile. So when we sketch this out, this is how this will look like. Okay. Right. So at the top, you have compression. At the bottom or at the other end, you can. So when it's compression, right? So the Y is where the material is. So when it's compression, the arrow will push towards the material. Compression. The Y-axis, repeat again, the Y-axis is the material. Okay, where the Y is the what? Material. Then at the other end is tensile. Tensile means from the material you get tensile. So this is how we draw our normal stress profile. And it's at this point over here, right, this location, Y location, this is where we call our neutral what? Axis.
Neutral axis.
Where our stress X is equal to what? Is equal to 0, right? So from here, the green line that we'll draw, this is the position of our neutral axis. And for this case, okay, for what I've drawn down here, this is also equal to our centroid. Okay. Not always the centroid is not always the neutral axis is at the centroid. I repeat again, not always the neutral. So the centroid is a geometry, right? I repeat again, the centroid is on geometry. The neutral axis is on stress. It's on stress field. I highlight that. Okay. Now, by looking at this structure, right, we all know that the structure will fail at point B. Okay. So I'm going to prove to you, or I try to highlight to you why this is so. Okay. So I want to next emphasize on the similar. Okay, I'm going to emphasize on a similar characteristic. And going to also introduce to you all the next big chapter that we're going to learn.